Okay, for this section, we're going to continue the discussion of maximum and minimum values of a function. The main results for this were presented in the flipped class video, so what we're going to do for this lecture is just work through a couple of more detailed examples than what were done in the flipped class video. So let's start with our first example. So let's find local max and mins for f of x being the function x over x squared plus 1. Let's also find where the function is increasing and decreasing, concave up and concave down, and any inflection points. Okay, so we know to find any of these things, we have to start with the derivative. So let's start with that. So we can use quotient rule on this. This is the derivative of the top, which is 1, times the bottom, times the top, times the derivative of the bottom, which is 2x, over the bottom squared. And now we can simplify this. So notice I get x squared plus 1 minus 2x squared over x squared plus 1 squared. This becomes 1 minus x squared over 1 plus x squared squared. And I can factor this as 1 minus x, 1 plus x over x squared plus 1 squared. And from this, we can see the derivative here never has a 0 in the denominator because x squared plus 1 is always bigger than or equal to 1. So in this case, our critical numbers, well, these are where the derivative is 0, and so these are going to be when x is equal to plus or minus 1. So what we can do then is we know that the sign of the derivative can only change as it goes through 0 from the intermediate value theorem. So we can go ahead and break our real line up into intervals where we exclude the places where the derivative is 0. So we'll go from minus infinity up to minus 1, from minus 1 to 1, and then 1 to infinity. So what we're using for the edge points of these intervals are plus or minus infinity, and then any critical numbers. So in this case, they're just where the derivative is 0. We might also, if the derivative were undefined, have to include those as well. Now what we're going to do is we're going to use all of the pieces that multiply together to give us our derivative. Now this last term we know is always positive, so technically you don't really need to include that, but we will. And so we'll make this table like this, and then we're going to check the sign of the derivative, or check the sign of each of these pieces to get the sign of the derivative. Now remember, it has to be positive, or always negative on each of these intervals, so we can pick any value to plug in. So for instance, if I plug in, say, negative 2, which is in this first interval, I would get 1 minus minus 2, which is positive. And then if I put in minus 2 to this, I would get a negative. This one's always positive. So if I take something that's positive times a negative times a positive, that gives me a negative. So that says my function's decreasing on this interval. For this next one, I could plug in 0. So 1 minus 0 is 1, which is positive. 1 plus 0 is 1 is positive. This one's always positive. We might as well fill those ones in. So we multiply a bunch of positive numbers together and we get a positive. So it's increasing on this interval. And then finally for this one, if I plug in 2, I get 1 minus 2, which is negative. 1 plus 2, which is positive. So this is negative, so this is decreasing. So from this we can see f is increasing, but only on this middle interval, so only from minus 1 to 1. And f is decreasing on the interval from minus infinity to minus 1 and from 1 to infinity. Notice we can also check the local max and local minimums, because if the function is decreasing from minus 1 to or from minus infinity to minus 1, and that switches to increasing, that means it's going down, and then it switches to increasing, so that has to be a local minimum. So the value x equals -1 gives a local minimum of, well, the local minimum is whatever the f value there is, so this happens to be -1/2. And conversely, for the next one, we're increasing and then decreasing, so that means we get a local maximum. So this is equal to +1/2. So that answers the first part here, where we've found the local maximums and local minimums, and we found where the function's increasing and decreasing. What we want to do next is look at concave up and concave down and any inflection points. So we know this means we need to look at our second derivative. So we're going to go ahead and differentiate. We'll use this one here to take the derivative of. So f double prime of x, well, this is going to be the derivative of the first term, or the top term, which is minus 2x times x squared plus 1 squared minus the top, and then the derivative of the bottom we have to use chain rule for, and then all of that over the bottom squared. So since it was x squared plus 1 squared, we square that and we get up to the 4th power now. And now we need to simplify this. So the first thing to note here is that I have an x squared plus 1 here, and an x squared plus 1 here, and then I have an x squared plus 1 here. So I can cancel those, and I'll get minus 2x left over from the first term times x squared plus 1, so we get rid of one of those. And then I have minus, and I combine that 2 and the 2x to get a minus 4x, and then 1 minus x squared all over. And now I'll have an x squared plus 1 cubed, because I've canceled one of those terms off. And now let's go ahead and simplify this, so I can factor out a negative 2x, and I will have left over x squared plus 1, and then minus 2, 1 minus x squared. It will become plus because we factored out the negative. X squared plus 1 cubed. Now we want to do some further simplification here. So I have minus 2x, and then I'm going to have x squared plus 1 plus 2 minus 2x squared all over x squared plus 1 cubed. We have to do all this simplification because remember, we're going to ask where this is undefined and where this is 0. So this becomes minus 2x, and in the parentheses here, I'm going to have a 3 minus x squared all over x squared plus 1 cubed. And now note again, the denominator here can never be 0 because x squared plus 1 is always bigger than or equal to 1. So if I factor this a little bit further, I have minus 2x, and then I'll have a square root of 3 minus x, square root of 3 plus x, and then x squared plus 1 cubed. And so the points where this is 0, so f double prime of x is equal to 0 when x is equal to 0 coming from the first term, or when x is equal to plus or minus root 3. And so now we'll make a table just like we did before. In this case, we're looking at the second derivative. So I'm going to have my intervals here. So I'm going to go from minus infinity to minus root 3, minus root 3 to 0, 0 to root 3, and root 3 to infinity. And then I'll put my minus 2x. I'll put square root of 3 minus x, square root of 3 plus x, 1 over x squared plus 1 cubed, and then f double prime, and then f is. So this, if we fill this in, this will be positive, positive, negative, negative. This will be I could have just put these together now, but this will be, if I have something less than negative root 3, this will be negative, and this will be, this will be positive, because negative, negative, this will be negative. This will be positive. So this is negative, and this is concave down. In this case, if I take something less than root 3 and subtract it, this will be positive, this will be positive, this is positive, this is concave up. And now this will be positive, because I'm subtracting something smaller. This will be positive, positive, negative, so concave down. And then finally, this will be negative, this will be positive. This will be positive. So I have a negative times a negative, so this is positive, so this is concave up. So from this, we see f is concave up on the intervals from minus root 3 to 0 and from root 3 to infinity. F is concave down on the intervals from minus infinity to minus root 3 and from 0 to root 3. And then we can see it changes from concave up to concave down. So the inflection points are when x is equal to minus root 3, because it changes from concave down to concave up. When x is equal to 0, because it changes from concave up to concave down. And then when x is equal to root 3, because it changes from concave down to concave up. Okay. So you can see these type of examples take a little bit of time to work with. And usually the main difficulty is actually doing this algebra to factor. That's where people tend to run into the issues. Taking the derivatives, most likely you're pretty comfortable with that by now. So let's try another example. Let's find the critical numbers. And local max / mins and intervals of increasing / decreasing for f of x equals x to the 4/5 times x minus 4 squared. Okay, so we start here just like before by taking the derivative. So we're going to use product rule for this. So the derivative of the first term is 4/5 x to the minus 1/5 times x minus 4 squared plus x to the 4/5 2 times x minus 4. And now the first thing to note is we can factor a 2x minus 4 out of both terms. And I'll be left with 2/5, and I'll have x minus 4 over x to the 1/5. So we're going to put this x to the 1/5 in the denominator, plus, and then I have x to the 4/5 left over here. Now I want to get a common denominator here. So this 2x minus 4 stays the same. And I'm going to have 2x minus 4, and then I have 5x to the 1/5. And so to get a common denominator here, I'm going to multiply the top and bottom by 5x to the 1/5. And notice that x to the 1/5 times x to the 4/5 just becomes x. So I get 2x minus 4, and then I have 2x minus 4 plus 5x over 5x to the 1/5. And so if I simplify this, I have 2x minus 4, and then here I'm going to have a 2x plus 5x, which is 7x, and then minus 8. And this is all over 5 x to the 1/5. So again, the algebra here is a little complicated. But other than that, it's pretty straightforward. Now, we do have a place where this is undefined. So the critical numbers here are, well, when x is equal to 0, the denominator is undefined. And then if x is equal to 8/7, we get a 0. And when x is equal to 4, we get a 0. So those are our critical numbers. Now we're going to take and break up the interval, the real line again, just like we did in the last example. So we're going to go from minus infinity to 0, 0 to 8/7, 8/7 to 4, 4 to infinity. And then we have our x minus 4 term. I guess we make it 2 times x minus 4. We have 1 over, let's say, 5x to the 1/5. And then we have 7x minus 8. So notice we're getting all of our terms here. And then we have our f prime. And then f is. So we plug in values again here. So we can see if we plug in something between minus infinity and 0. So say minus 1. This will be negative. This will be negative. This will be negative. And then this would be positive. This is negative, positive, positive, positive. So remember, we're just picking something in the interval. So for example, the 0 to 8/7, I could just pick 1 in there and plug it into here. And so I have 1, say 1 over 5 times x to the 1/5, which is just 1/5, which is positive. And this is negative, negative, positive, positive. This becomes negative, positive, negative, positive. So this is decreasing, increasing, decreasing, increasing. And so from this, we can see when x is equal to 0, this gives us a local, we're going down and then up. So this is a local minimum. X equals 8/7. We're going increasing and then decreasing. So that gives us a local max. And then x equals 4. We're decreasing and then increasing. So this gives us a local min. So the other concept we talked about was absolute maximums and absolute minimums. And for that, we used the extreme value theorem that said on a closed interval, we always have an absolute maximum and an absolute minimum. So let's see some examples for how we do this. So let's find the absolute maximum slash minimum of, let's say, f of x is equal to x cubed minus 6x squared plus 5. And let's say we're looking at this on the closed interval minus 3 to 5. So we know if it's a closed interval, we always have an absolute maximum and an absolute minimum. If it's not a closed interval, we might have one, we might not. So our first step is to find the critical numbers. So we take the derivative. This is just 3x squared minus 12x. So I can factor 3x out of that. And I just get 3x times x minus 4. This derivative is defined everywhere, so our critical numbers are just where it's equal to 0. So that's when x is equal to 0 or when x is equal to 4. And so now we take and we plug these and the endpoints in. So I have f of 0. Well, we just plug this into the original function. So for this is just 0 cubed minus 6 times 0 squared plus 5, which is just 5. And we do the same thing for the other critical value. This gives me minus 27. And then we have to also plug in our endpoints of minus 3 and 5. If I plug in minus 3, I get minus 76. And if I plug in 5, I get minus 20. So then that tells me my absolute max is the largest value on this list. So this is 5 at x equals 0. And my absolute minimum is the smallest value on this list. So this is minus 76 at x equals minus 3. Okay, so notice we don't have to worry about increasing, decreasing, or second derivative test or anything like that for here. We just plug in the values and see which is the biggest and smallest when we're trying to find absolute minimums and absolute maximums. So let's try one more example that's a little bit more complicated. Okay, so we want to find the absolute maximum and absolute minimum of this function f of t, which is 2 cosine of t plus sine of 2t. And we want this on the closed interval from 0 to 2 pi. So just like we've started the other ones, we start by taking the derivative. So we know the derivative of cosine is negative sine. And then we have to use chain rule for the second part, so we're going to get cosine of 2t times 2. And so now we can see f prime of t is equal to 0 when, well, if we set this equal to 0, and then we can, so this would be when minus 2 sine t plus 2 cosine of 2t is equal to 0, which is the same as when 2 cosine of 2t is equal to 2 sine of t. We can cancel those 2's out, so I have cosine of 2t is equal to sine of t. And now this isn't so obvious how to solve this, so what we can use is we can use a trig identity. Again, I wouldn't expect you to remember this, but maybe remember that there is one that you could look up. So this is 1 minus 2 sine squared of t. So if I plug that in, I get 1 minus 2 sine squared of t is equal to sine of t. And so bring everything to one side, so I have 2 sine squared of t plus sine of t minus 1 is equal to 0. And now I can factor this of 2 sine t minus 1 sine of t plus 1 is equal to 0. So this is going to be true. This means we want 2 sine t minus 1 equals 0, or sine t plus 1 equals 0. So this one leads to sine of t equals 1/2, and this one leads to sine of t equals minus 1/2. However, remember, when we started this problem, we're only looking on the interval from 0 to pi over 2. So if we think about this on the unit circle, that's just this part here. So this one will never happen on the interval we're interested in. So we can ignore that one. And then we know sine is the y value, so that's going to be the value here. And so sine of t equals 1/2 when t is equal to pi over 6. And that's the only value that works on the interval from 0 to pi over 2. So our critical numbers is only t equals pi over 6. So now we need to evaluate our function at that. So f of pi over 6 is 2 cosine of pi over 6 minus sine of 2 times pi over 6. This is 2 times square root of 3 over 2 minus sine of pi over 3. So this is 2 square root of 3 over 2 minus square root of 3 over 2, which is square root of 3 over 2. And now we also have to evaluate at the edge points. So f of 0 is going to be 2, and f of pi over 2 is going to be 0. So this tells us our absolute maximum is 2 at t equals 0, and our absolute minimum is 0 at t equals pi over 2. So what we'll really use this for isn't the way you actually encounter this in a calculus class. You might just be asked to find the absolute maximum, absolute minimums, or local max and local minimums with just some equations given. But what we'll see is we're going to actually use this in optimization problems. So we'll see often we're interested in finding maximums and minimums of actual functions that represent things occurring in the real world. So that's what we'll look at in the section on optimization.